derivative of dt2 dt2 of this vector function. Now you have checked that in book, Ghoshmaiti book, they have used for vector r, they didn't use the arrow which I am using here. They just use the bold r, written it bold in bold form. So you can use any one of the notations. Both are correct. I found this one is easier to write. So I'm using this arrow. Both are correct, okay? So now try to find d2 dt2 of this vector function. Now that means ddt over ddt of this whole function, right? Now check that function. What we can write this function? We can write it as the box of r dr dt d2r dt2, right? This is from the definition of box product. Now we know what is the derivative of a box product. Just we have to find the derivative of each of the components single time, then add them. So we will get, there will be total 3 components. At first derivative of this one, that is under box dr dt, keeping the other two as same, plus keeping first same, derivative of the second one, keeping the third one same, plus for the third one t3. That's it. Now check the first component. It will be eventually, its value will be 0 because 2 components are same. Similarly the second part, this and this are same, so it will also be 0. So there will be only one part, which is equals ddt of this. Right? Now apply ddt over it. So what will we get? Derivative of the first component, which will be dr dt, that is r dashed, then keeping the remaining two as same, so r dashed, r triple dashed, then plus r double dashed, r triple dashed, plus r dashed, and r fourth. This one obviously 0 because first 2 components are same, but these two are non-zero. So its value will be r dashed, r triple dashed, this one, plus r dashed, r fourth derivative. This is the required result. Now trying to find few more derivatives. Next one is question number 5I. Find the derivative with respect to t of the vector r square plus 1 by r square. That is ddt of this one. What will be its derivative? 2r dr dt, and for its minus 2 by r cube dr dt. Just like the concept from analysis, real analysis. This taking common 2, it will be r minus 1 by r cube dr dt. That's it. This is the required result. Now moving to the next example, question number 7C. If r equals, the vector r equals a cos t I cap plus a sin t j cap plus bt k cap, then show that this box product r dashed, r double dashed, r triple dashed equals a square b. So at first we need to find out r dashed, r double dashed and r triple dashed. Let's find it out. R dashed, it will be just the derivative of its components, so it will be minus a sin t I cap. plus a cos t j cap plus b k cap. Then r double dashed, it will be minus a cos t I cap minus a sin t j cap, and the remaining part is 0, remaining next component. And r triple dashed, it will be minus plus a sin t I cap minus a cos t j cap. Okay, now try to find the box product. What will be its box product? Box product is r dashed of r double dashed and r triple dashed. That means r dashed dot r double dashed cross r triple dashed. So how to find this one? Starting with this r double dashed cross r triple dashed. That means I, j, k. Just try to find the cross product of two vectors, and it will be minus a cos t, first component of r double dashed, then minus a sin t, and this is 0. Next a sin t minus a cos t and 0. Now expand the determinant. I am trying to expand it with respect to the third row. It will be easier because the two components are 0 of this third column, not third row. I am expanding this determinant with respect to third column. This and this are 0, so there will be only one value, that is k cap into a square cos square t plus a square sin square t. So it will be a square k cap. Now we are trying to find r dashed dot this r double dashed cross r triple dashed. What is our r dashed? R dashed is minus a sin t comma a cos t comma b dot this value, that is a square k cap. That means what will be its components? Its components will be 0, 0, a square. Now what is the dot product? Multiply just the sum of product of each component, that is this into this, which is 0, then this into this, which is 0, and the last one is b a square, that is a square b. This is our required result of the given box product. Next problem is exercise question number 8. This type of examples using this velocity and acceleration, like the concepts from physics, these are very important. We will also solve it few more examples using this type of velocity and acceleration related problems in the next chapter also in integration. Now we have one problem using this, saying that if r is the displacement vector at any time t of a moving point, suppose this is our origin, a point is moving, and it is saying r is the displacement vector at any time t of a moving point. Suppose the point is here, p. So its position vector or the displacement, this is r. That means from here we can write OP equals r, and this is at the time some t time. Okay. Then its velocity vector v is denoted by dr dt. We all also know that v is velocity, it is denoted by dr dt. And its acceleration generally denoted by f, it is denoted by d2r dt2. Okay, we have this one. Now it is saying that at an instant t of the vector from the origin of a moving point is r equals a cos omega t plus b sin omega t, where a and b are constant vectors. A and b are constant vectors and omega is a scalar. Then find its velocity. And prove that r cross v is a constant vector and show that its acceleration is towards origin. Towards origin. So let's try to find out that v and f. We know v is dr dt and f is d2r dt2. We have the value of r, so we can easily find out v and f. So in the next line we are writing v equals dr dt. What will be its value? It will be minus a omega sine omega t plus b omega cos omega t. This is our velocity at any point t. Next is acceleration f, which is equals d2r dt2. So its acceleration, now again find its derivative. So it will be minus a omega square cos omega t minus b omega square sine omega t. Now if you take common minus omega square, it will be a cos omega t plus b sine omega t. That means ultimately our r. So we can write it as minus omega square r. Now check what we have to prove. We have to prove that the question was prove that its acceleration is towards origin. Here we get that f equals minus omega square r cap. This one. This is obviously a constant, right? And minus constant, because omega square, this is positive, so minus omega square is obviously negative. Now starting from the diagram. This is O origin. A point is start to move from this point at some instant time t. It is at the point P, and whose vector is denoted by r vector, that is OP equals r. So that means the direction of r is always like this direction. R is increasing in this direction. Now we have found that at any instant t, that is at the point P, the acceleration f is minus omega square r. That means its direction is always opposite to r, because it is multiplied by some negative quantity of r. That means what is the direction of r? This direction. So its opposite direction will be this direction. That means the direction which is towards the origin. So from here we can claim that its acceleration is towards origin. Okay, this proves the second part, and there is one more part which we have to prove, that is r cross v. Prove that r cross v is a constant vector. So let's try to find out r cross v. What was our r? R was a cos omega t plus b sin omega t cross v was minus a omega sin omega t plus b omega cos omega t. That was b. Now we can apply that determinant form ijk, because we don't know what are the components here. We have only get a vector, b vector. So we just have to multiply normally, like multiply this and this, cross product of this and this, plus cross product of this and this, plus cross product of this and this, then this and this, like this. So it will be at first minus a cross a omega cos omega t sin omega t, then minus this and this, we are multiplying this two, finding the cross product, a cross b, sorry, b cross a. It will be b cross a cross b will be different thing, because cross product are not commutative. So b cross a, then omega sin square omega t, then next part is a cross b omega cos square omega t plus b cross b omega sin omega t cos omega t. Now check, a cross a is 0, b cross b is 0. So these two terms will be vanished in the next step. So in the next step we are writing this one and this one. That was minus b cross a. In the next line we can write is plus a cross b. So this and this will be similar. So I am writing in the next line equals a cross b plus a cross b omega sine square omega t plus a cross b omega cos square omega t. Now take common omega a cross b, then sine square t plus cos square t. This will be 1. So the result is this. Now a and b both are constant vectors. That means their cross product is also a constant vector. So the whole thing is a constant vector. This proves the second result also. And apart from this example, we have two standard theory also rather than standard condition which will be needed. These are two necessary and sufficient condition. Number one is when a vector f, vector function ft, it is of constant length. That means its magnitude is constant. It is of constant magnitude. Then f dot df dt is 0. And when f is of constant direction, that means it is always parallel to some fixed line. Constant direction means always parallel to some fixed line, or we can write this one as also parallel to a fixed line. Then its condition is f cross df dt, this will be a 0 vector. These two are standard conditions.